Welcome, ladies and gentlemen, to this presentation entitled Quasi-static Compliance Calibration of Industrial Manipulators. This presentation documents the results of the COMACH Project's Task 3.1 Robot Stiffness Identification Procedure, which is a part of the Robot Accuracy Increasing System. This work is presented at the final meeting of the Swedish Product Consortium, consisting of Hexagon, ABB and KTH, together with representatives from Vinova, in November 2021. My name is Nicholas Theissen and I co-author this work with my colleagues Monica Catharina Gonzalez and Theodoros Laspos under the supervision of Professor Andreas Akenti. This presentation consists of 4 sections. The introduction section focuses on the goals of the COMACH project and relates them to performance criteria and test methods according to ISO 9283. These can be used to quantify the capability of an industrial manipulator when the robot is carrying a payload, and other performance criteria such as quasi-static deflections, which can be used to assess the robot in contact applications. The main section is the methodology section. It presents measurement instruments and procedures for both the static and quasi-static deflection of industrial manipulators. The results and discussion section focuses on the application of the proposed comparison implemented in a case study on a large-sized serial articulated industrial manipulator in 5 different positions of its workspace at KTH. Then it explains how the data can be used for compliance calibration. This presentation ends with a summary of the work conducted in the field of quasi-static compliance calibration, as well as an outline of ongoing work. It outlines its opportunities and limitations, as well as the next steps to support compliance calibration. Introduction. COMACH Task 3.1. The parties responsible for the coordination of this work are KTH in close collaboration with ABB and Hexagon. The compliance calibration procedure, together with the compliance compensation system, should ensure an average positioning accuracy under load better than 0.25 mm. This task focuses on the definition of an offline compliance calibration procedure for articulated industrial robots. The core elements of the task are the robot modeling and measurement, which is the process of defining an appropriate mathematical model and then identifying the different model parameters such that the model describes the actual robot as good as possible. It must balance the detailed representation, which enables a good prediction, and practical identification, curbing the number of model parameters. ISO 9283. According to the information provided by the International Federation of Robotics, most industrial manipulators are used in tasks in which the manipulator carries a payload. In this case, kinematics, gravity torques and controller settings are the most important performance criteria to assess the applicability of an industrial manipulator for its intended purpose. The tasks are reflected through performance criteria such as the pose as well as path accuracy and repeatability. These indicators are commonly stated in the product descriptions of the manufacturers of industrial manipulators. Poses are measured at targets with a static manipulator, while paths are measured under motion with the manipulator following a trajectory. Figure 2 visualizes potential poses and paths according to the recommendations by the ISO standard. However, these performance criteria, according to ISO 9283, are less informative when the manipulator is engaged in contact applications such as metal cutting. Contact applications. Metal cutting, such as trimming, grinding or deburring, can be considered as contact applications. There exists no standard about the evaluation of performance criteria of industrial manipulators in contact applications, as it is only a minor share of manipulators that is installed for that purpose. Of the shipments of industrial robots from 2011 to 2015, it was only approximately 1% of the robots that were installed for metal cutting as the intended use. Due to the absence of a standard, researchers are inspired by the state-of-the-art of performance evaluation of lathe and machine tool. One of the main criteria under investigation is compliance or stiffness. The stiffness of a mechanical system can be defined as its capacity to sustain loads and it can be quantified through modeling or measurement. A priori modeling approaches employ finite element analysis. These are usually reserved for robot manufacturers and researchers. Then there are a posteriori measurement approaches to evaluate compliance. There are online approaches that identify the stiffness of an industrial manipulator from features of machined workpieces, and there are offline experimental approaches. This work focuses on offline experimental approaches. Serial articulated manipulators in quasi-static contact applications. ISO 9283 provides guidelines for the measurement and evaluation of static compliance. This is representative of a robot carrying a payload. However, this work intends to emulate the quasi-static component of a metal cutting process. The quasi-static component of the process force consists of the slow and periodic force with a frequency lower than approximately 0.5 Hz. This quasi-static component is qualitatively highlighted in Figure 4. This concludes the introduction section. Methodology. Measurement instrumentation. The conceptual measurement setup can be seen in Figure 5 on the right-hand side. The setup comprises the following equipment. Number 1, a large-size serial articulated industrial robot with its corresponding controller, which is not included in the picture. Number 2, a Leica 8901 long-range laser tracker, not included in the picture but symbolized through the 0.5-inch spherically mounted retroreflector. The measurement instrument loaded double ball bar. Number 4, a rigid table link. And number 5, a dummy end effector with tool center point and mechanical interface for the spherically mounted retroreflector. The deflection measurements are performed with two different metrology loops. The first metrology loop uses an LVDT for the deflection measurement. The second loop uses the laser tracker. Measurement process. The procedure for both the static and quasi-static measurement is repeated at 5 positions, numbered as circles 1 to 5. The circles have different distances, r, from the origin of the robot's base coordinate system. This is visualized in Figure 6. All circles have the same z-axis component, or height. The circles have a diameter of approximately 250 mm. For the static measurement, the manipulator moves to a static configuration, then the robot is loaded with a force, then the robot is unloaded after the deflection has been measured. Finally, the robot moves to another static configuration, then the procedure is repeated. The static measurement measures the static deflections at 37 index positions along a circular trajectory. This is indicated in the circle on the right-hand side in the top corner. For the quasi-static measurement, the manipulator moves to a start configuration, then the robot is loaded, then the manipulator moves along a circular trajectory, and only after completing the circular trajectory, the robot is unloaded. This dissected the circle into approximately 16,000 measurement points. Both measurements induce loads of 125, 250, 375 and 500 Newton. For both the static and the quasi-static measurement, multiple force components were exerted simultaneously. The task program used for the static and quasi-static trajectory are highlighted below in rapid instructions. Video 1 shows both the static and the quasi-static measurement procedure. The static measurement procedure can be described as the move, load, unload, move sequence. The robot moves to a configuration, then it gets loaded, the deflection is measured, it gets unloaded, and then it moves to the next configuration. And the process is repeated. In the quasi-static case, the manipulator executes a trigger movement by moving 1 mm up and down at the start point of the circle with a velocity of 250 mm per second. Then the manipulator moves 2 times clockwise about the same circular trajectory. The circles were measured with an angular overshoot of 180 degrees to exclude transit effect from the measurement data. The manipulator followed the trajectory with a Cartesian velocity of 50 millimeters per second. At this velocity, dynamic effects can be assumed negligible. Both the laser tracker and the LVDT are set to continuous data recording at 1000 Hz. Data analysis. The deflections delta x are calculated as the position differences of the loaded tool center point position xij and the reference tool center point position xiref at a load of 125 Newton. The indices I and j represent the positions and the loads along the circular trajectory. There are 37 static configurations and 15,899 quasi-static configurations. All deflections are calculated relative to a reference load of 125 Newton to remove the influence of play in the setup, the kinematics of the manipulator, as well as backlash in the manipulator. For the quasi-static deflections at the I-TCP positions, first the angular overshoot needs to be removed, then the difference can be calculated. In both the static and the quasi-static case, the measurement from the LVDT needs to be compensated for the deflection of the table link. The magnitude of the deflection, which is referenced in the subsequent section, is calculated as the Euclidean norm of the deflection. In the following section, the wording apparent load is used to highlight the idea that at an apparent load of 125 Newton, the system is loaded with 250 Newton, but the difference is calculated with respect to the reference load at 125 Newton. Results and discussion. The magnitude of the static and quasi-static deflections along circle 2 for apparent loads of 125, 250 and 375 Newton can be seen in the tables on the bottom. The magnitude of the deflection, as one would expect, increases with the load, but also changes along the circular trajectory as the Cartesian stiffness of the industrial manipulator depends on the configuration. The tables show the apparent load, the static deflection as measured by the LVDT and the laser tracker, the quasi-static deflections as measured by the LVDT and the laser tracker, as well as their quotient. The measured quasi-static deflections are on average approximately 22% bigger than the measured static deflections. The quasi-static deflections are at most 32% bigger than the static deflections. For all acting loads and all circles in the case study, the quasi-static deflections are bigger than the static deflections. The data have been measured using the LVDT as well as the laser tracker. The difference in the measured LVDT and the laser tracker data can be accounted for by the distance between the two measurement points. The static and quasi-static deflections are very similar in their characteristics, but they differ in their magnitudes. Compliance calibration. The compliance model relates the loaded to the unloaded end effector pose for a configuration of the robot under the consideration that an external force is applied in a linear stress-strain region, that is, the deformation of the structural loop components due to their finite stiffness is linear. This work uses a compliant manipulator model based on rigid bodies with flexible joints, also called a lump parameter model. The joints can be represented as linear elastic torsional springs. This simple stiffness parametrization lumps together several non-kinematic error sources such as the link deformations as well as motor and gearbox friction, as they will affect the measurement data. The joint stiffness values are identified based solely on the measured translational displacements without accounting for the rotational displacements. For each tuple consisting of the configuration in terms of the joint angles, measurement points as well as wrench and deflection vector, a joint stiffness matrix can be identified. A linear least square parametrization is used to optimize the parameters over the measured joint angle domain. The identified joint stiffness matrices in terms of the static and the quasi-statics for circle 1 to circle 5 reflect the difference in the deflections as a loss of apparent stiffness, as can be seen in Table 5. This was expected as the magnitude of the deflections affects the identified joint stiffness values linearly under the assumption of invariant configurations and wrenches. Table 5 displays the norm of the stiffness matrices as well as the relative difference between the static and quasi-static stiffness matrices for the same circle. Outlook. Measurement of a KUKA, Stäubli and ABB robot. For further analysis, static and quasi-static deflections of industrial manipulators of 3 different robot manufacturers were measured. All measurements are performed with different apparent loads. The circles are positioned at different positions of the working space, while all robots were programmed to perform quasi-static trajectories at a velocity of 50 mm per second. As one can see from the summary of the experiments in Figure 10, also the KUKA and Stäubli robot, the quasi-static deflections are significantly bigger than the static deflections. Also, in these cases, it appears that the deflections have the same trends in the workspace, however, their magnitudes differ. Furthermore, one can see that the deflections vary significantly among the industrial manipulators. Please consider that none of these measurements provides the best approximation of the manipulator's stiffness, as the structural loop features different end effectors, resulting in different system stiffnesses at the tool center point. Error separation analysis. The results displayed in this presentation imply that there can be significant differences in the magnitude of the static and quasi-static deflections of articulated manipulators. Thus, KTH, ABB, Mondragon University and Ideco started a collaboration for an error separation analysis to quantify the influence of velocity, control parameter settings, as well as the magnitude of internal and external torques on the static and quasi-static deflections of industrial manipulators of 3 different robot manufacturers. The quasi-static measurement procedure seems a more applicable evaluation method to represent the actual manipulator more accurately for manipulators moving at low velocities. This means that the compliant quasi-static robot model, that is the robot stiffness model which is derived from a quasi-static measurement, may yield more accurate estimates for the trajectory optimization compared with static stiffness in the implementation phase of manipulator calibration. This may facilitate a pragmatic compliance calibration of industrial manipulators. The pragmatism in that sense lies in the possibility to calibrate an industrial manipulator task-dependent, meaning that in the relevant portion of the workspace with loads in the magnitude of the task. This may make compliance calibration cheaper, faster, and potentially more accurate. This concludes this presentation. Thank you very much for your kind attention.